Okay, folks, it's that time of the day, and I'm going to go ahead and get started. The very first thing I want to do is I want to remind you about valence electrons and how to determine the number of electrons in the outermost shell. With your main group elements, that's groups 1 and 2 and group 13 through 18, the number of valence electrons is going to equal the last digit of the group number. So with hydrogen and lithium, for example, they're in group number 1. The last digit is a 1, so they have 1 valence electron. With boron and aluminum, they're in group 13. The last digit is a 3, so they have 3 valence electrons. Fluorine, chlorine, bromine, they're in group 17. The last digit is a 7, so they have 7 valence electrons. Neon, argon, krypton, they are in group 18. The last digit is an 8, so they have 8 valence electrons. So again, with your main group elements, groups 1 and 2, and group 13 through 18, the number of valence electrons is going to be equal to the last digit of the group number. Now with your transition metals, because the transition metals are in the N-1D subshells, the majority of transition metals wind up only having 2 valence electrons. The exception to that are the anomalies. And as a reminder, the anomalies are group 6 and group 11. And for group 6 and group 11, they only have 1 valence electron. So that is your valence electrons. Now, the reason we're going over the valence electrons is because when we start talking about the Lewis structures of atoms, of elements, the Lewis structures of ionic compounds, the Lewis structures of covalent molecules, the electrons that we're going to be working with are going to be the valence electrons. They're the electrons that are responsible for the element's reactivity. So we are going to be focused on the valence electrons. Now, to develop the Lewis structure of an atom of an element, we start by writing the element's symbol, and that symbol represents the identity of the element, but it also represents the core electrons of that element. Once we've written the symbol, we illustrate the valence electrons as dots. And these dots are placed around an imaginary square that surrounds the symbol. With respect to the dots, we will add 1 dot to each side of the square before pairing them up. So what I'm going to do is I'm going to take a few minutes and we are going to develop the Lewis dot structure for an atom of an element. And we're going to do so by determining the number of valence electrons for that element and then placing those valence electrons as dots around an imaginary square that encompasses the symbol. So let's take group 1. In group 1, you have hydrogen. Hydrogen is in group 1. The last digit is a 1. So hydrogen has 1 valence electron, which we're going to illustrate as a dot around the symbol. Lithium. Lithium was in group 1. The last digit is a 1. So it has 1 valence electron, which we're going to illustrate as a dot around the symbol. Let's talk about beryllium. Beryllium is in group 2. The last digit is A2, so it has 2 valence electrons. We're going to place 1 valence electron around on each side of an imaginary square until we get to that 2 valence electrons. Let's move over to boron. Boron is in group 13. The last digit is a 3, so it's going to have 3 valence electrons. Again, you're going to place 1 electron on each side of an imaginary square that encompasses the symbol. Let's look at carbon. Carbon is in group 14. The last digit is a 4. We're going to place 4 dots around the carbon symbol. And those 4 dots are going to occur so that there is 1 on each side of the symbol before pairing. So with group 17, let's look at chlorine. Chlorine is in group 17. The last digit is a 7, so it has 7 valence electrons. You're going to place 1 electron on each side of the atom before pairing those electrons to give you your 7 valence electrons. Any questions about how to develop the Lewis dot structure of an atom of an element? Okay. So then let's look at the Lewis structure of an ionic compound. Yesterday, I reintroduced the idea of an ionic compound. An ionic compound is going to contain an ionic bond. An ionic bond is essentially a magnetic attraction between a positively charged cation and a negatively charged anion. Now, the cation is the result of an element losing its valence electrons to become positively charged. When we look at cations, we're going to be mainly focused on the metals. Your anions are going to result from an atom of an element gaining additional valence electrons to obtain a noble gas configuration. The number of electrons that the atom is going to gain is going to be the quantity needed to reach 8 valence electrons, otherwise known as an octet. And again, with an anion, this gaining of valence electrons to form this octet is going to result in a negatively charged ion because you're gaining negatively charged subatomic particles. Now, when we develop a Lewis structure for an ion, whether that's an ion in an ionic compound or later when we talk about polyatomic ions. When we develop the Lewis structure for an ion, the Lewis structure of the ion is placed in brackets with the charge shown as a superscript to the right of the bracket. So let me just illustrate what's going on with ionic compounds. We've been talking a little bit about ionic compounds. We're going to talk about them more on Tuesday of next week. So let me illustrate more about what's going on with an ionic compound. The first example that I'm going to do is I'm going to work with sodium chloride. Sodium is in group 1. The last digit is a 1. So sodium has 1 valence electron. Chlorine is in group 17. The last digit is a 7. So your chlorine is going to have 7 valence electrons. You're going to place 1 on each side before pairing them up. And by the way, it doesn't matter where you start placing your electrons. All that matters is that you're placing 1 on each side of the atom before pairing it. On each side of an imaginary square. Now, sodium being a metal is going to lose its electron, and chlorine being a nonmetal is going to want to gain electrons. The sodium will lose its valence electrons, and the chlorine is going to gain valence electrons till it achieves an octet. So what is left is you have sodium that is positively charged with no valence electrons, and you have chlorine, and the chlorine has now 8 valence electrons and is negatively charged. Once you've created these ions, there is going to be an electrostatic attraction that occurs between these atoms. And so what we wind up doing, again, when we're developing Lewis structure of ions, the ions are placed in brackets with the charge as a superscript. And that is true for both the cation and the anion. And basically, this electrostatic attraction is like a magnet. It brings that cation and that anion together. Let's look at barium oxide. Barium is in group 2. The last digit is a 2. So barium oxide has, has 2 valence electrons. Oxygen is in group 16. The last digit is a 6. So oxygen has 6 valence electrons. Barium being a metal is going to donate its valence electrons. Oxygen being a nonmetal is going to want to gain those valence electrons until it achieves an octet. So since barium has lost its two valence electrons, it now carries with it a 2 plus charge because it's lost those negatives. And oxygen, because it has gained those electrons, takes on a 2 negative charge. Notice that the oxygen has an octet now. Now, once these charges are made, there is going to be an electrostatic attraction between the cation and the anion to make barium oxide. Now, to illustrate it properly, we're going to place the ions in brackets with the charge as a superscript outside of the bracket. And this would be the structure for barium oxide. Now, up until this point, I've used ionic compounds that occur in a 1-to-1 ratio, but that is not always the case. An example would be aluminum oxide. So let's look at aluminum oxide. So aluminum is in group 13. And so our aluminum atoms have 3 valence electrons. But there are 2 aluminum atoms, each having 3 valence electrons. Oxygen is in group 16. The last digit is a 6, so each oxygen has 6 valence electrons. Now, aluminum, being a metal, is going to lose its valence electrons. Oxygen, being a nonmetal, is going to gain valence electrons until it achieves an octet. So our aluminum is losing its valence electrons. And the oxygen is gaining those electrons. So what we have is we have 2 aluminums that have lost their 3 valence electrons, and hence they are 3 plus. And we have 3 oxygens that have gained 2 valence electrons each in order to give those oxygens an octet. Now, you can represent this as each individual atom, or you can represent this with a simplified version where you place the aluminum in brackets with its charge as a superscript, and the oxygen in brackets with the charge as a superscript. questions? So let me stop share temporarily. Okay. The next thing we're going to do is we're going to get into Lewis structures of covalent molecules. But to introduce the Lewis structures of covalent molecules, I'm going to start by introducing the Lewis structures of diatomic elements. Diatomic elements being examples of covalent molecules. Now, because we haven't gotten to this in class, there are 7 diatomic elements, meaning there are 7 elements that when found in nature will always, all by their little lonesomes, will always come in pairs. And they follow the line of Brinkelhoff: bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. What it means is that if you find bromine all by its little lonesome in nature, it will be in the form of Br2. What it means is that the oxygen that you breathe in, found in nature, is in the form of O2. So these elements are called diatomic elements because di means 2, atomic atom, so 2 atom elements. Now again, these are examples of covalent molecules. Covalent molecules contain a covalent bond. A covalent bond arises through the sharing of electrons between 2 atomic nuclei. Folks, this is different than what we just did with ionic compounds. With ionic compounds, the metal gave up its electrons. The non-metal absorbed those electrons. In a covalent bond, the electrons are shared. These shared electrons are going to be represented with a line. Now, how do you know that you're working with a covalent molecule instead of an ionic compound? Covalent molecules consist of nonmetals and metalloids only. So again, I'm going to introduce covalent molecules by working with the diatomic elements. Specifically, I'm going to work with hydrogen, oxygen, and nitrogen as my examples. So hydrogen. Again, hydrogen is in group 1. It has 1 valence electron. Now, in the diatomic molecule of hydrogen, that means we have 2 hydrogens, each with their own valence electron. Now, once again, covalent bonds arise through the sharing of electrons. So the hydrogen on the left is going to share its electron with the hydrogen on the right. Notice they're not giving away their electrons. So what we see is that we obtain this structure. Now, the hydrogen on the left deems itself as having 2 valence electrons because it believes that the share of electrons belongs to it. The hydrogen on the right also sees itself as having 2 valence electrons. The maximum number of electrons that a hydrogen will share is 2. Now, we represent, as I mentioned on the second point associated with covalent, we represent these shared electrons as a line between the 2 atomic nuclei. So that line means that there are 2 dots. Now, it is more common for atoms to share 8. In fact, when we talk about covalent molecules, it is going to be a rare occurrence, very rare occurrence, where the nonmetals and metalloids do not have 8 valence electrons around them. There are 2 exceptions to that, and that is going to be hydrogen, which, as I said, the maximum it will ever have is 2, and then boron, which will typically have 6. But for all other nonmetals and metalloids, if you are dealing with a covalent compound, it is going to be an extremely rare occurrence for them not to have an octet. They want a share of 8 minimum if possible. So let's look at oxygen with this new piece of information in mind. Oxygen is in group 16. The last digit is a 6, so it's going to have 6 valence electrons. There are 2 oxygen atoms. Now, oxygen is going to start by sharing 1 pair of electrons. When it shares the 1 pair of electrons, the structure that evolves is this structure. Now, keeping in mind, does everybody have an octet? Let me show this as dots for now. It'll make it easier. Well, on the left-hand oxygen, it currently only has 7 valence electrons. It is not happy because, with a rare exception, they want a minimum of 8. The right-hand oxygen has 7 valence electrons. So this oxygen is not content. So it's going to share another pair of electrons between the 2 atomic nuclei. Once it does so, the left-hand oxygen sees it sharing 8 valence electrons. The right-hand oxygen also sees it owning 8 valence electrons. It is happy because it has an octet. So oxygen is going to share 2 pairs of electrons, which is represented with 2 lines. Let's look at nitrogen. Nitrogen is a group 15 nonmetal, which means it's going to have 5 valence electrons. Nitrogen is going to start out by sharing 1 pair of electrons between the 2 atomic nuclei. When it shares that pair of electrons, each nitrogen views itself as having 6 valence electrons. But again, it is going to be the very, very rare occasion that an element does, or that a nonmetal or metalloid does not have a minimum of 8. So this nitrogen is not content. So it's going to share another pair of electrons between the 2 atomic nuclei. When it does so, this structure evolves. The left-hand nitrogen sees itself as owning 7 electrons. The right-hand nitrogen sees itself as owning 7 electrons. Again, it's very, very rare for a nonmetal or metalloid not to have a minimum of 8 valence electrons. So this nitrogen is not happy. It is going to share another pair of electrons between the 2 atomic nuclei. In so doing, now the left-hand nitrogen sees itself as owning 8 electrons. The right-hand oxygen sees itself as owning 8 electrons. It is happy. Therefore, our nitrogen is going to share 3 pairs of electrons between the 2 atomic nuclei. Because in so doing, it gets an octet. Questions so far? This brings up some more terminology. First of all, we've talked about shared electrons, and what isn't shared would be considered unshared electrons. A shared pair of electrons is considered a bonding electron. An unshared pair of electrons are considered to be non-bonding groups or lone pairs of electrons. Now, these bonding electrons come in specific types of bonds. If one pair is shared between 2 atomic nuclei, it is called a single bond and is represented by a single line between the 2 atomic nuclei. If 2 pairs of electrons are shared between the same 2 atomic nuclei, it is called a double bond, and it is represented by 2 lines or an equal sign. If 3 pairs of electrons are shared between the same atomic nuclei, it is called a triple bond, and it is represented by a triple line. So let's look back at our diatomic elements. Hydrogen has a single bond and no lone pairs. Oxygen consists of a double bond and each oxygen has two lone pairs. And finally, our nitrogen consists of a triple bond and each nitrogen has one lone pair. This is a good spot for us to take a break. When we come back, we are going to start developing the Lewis dot structures for covalent molecules that are not the diatomic elements. We are going to apply a set of rules that they are a set of steps that can be applied to every single molecule. Now, this morning, I should say, if you look in your Blackboard, in this week's folder, under the optional homework and answer keys, at the very bottom, you're going to see something called the Lewis structure handout. That Lewis structure handout has the step-by-step process that I am going to follow for the rest of the afternoon. I am going to do a variety of molecules, and we're going to talk about simple covalent molecules, and we're going to talk about resonance structures today. And then next Wednesday, we're going to talk about the expanded octets, but we've still got a good hour worth today. So again, we're going to take a 15-minute break. So let's be back here at 12:15 and we'll pick up from there. Okay, so let's get back at it. Right before we left for the break, I said that there was a document that I put into the homework folder that for this week that marked or gave you the process for determining the Lewis dot structure associated with a variety of molecules. The document will look a lot like the one that I have pulled up. Basically, in step 1, we are going to determine the total number of valence electrons. Now, we're going to do so for a neutral atom, and then at the end of class, we're also going to do so for an ion. For a neutral atom, you're simply adding up the valence electrons of the atoms of the element. But for an ion, you also have to take into account the charge on that ion when you're adding up the valence electrons. Once we add up the valence electrons, we're going to develop the skeletal structure. Basically, we're going to determine who the central atom is, and then we're going to place all other elements around that central atom. Now, there is a fairly official rule out there that says the least electronegative atom will be the central atom. But it's actually my experience that chemical formulas make it fairly easy to determine the central atom because it's usually the first element listed in the formula. Now, the exception to that is if the first element listed in the formula is hydrogen. Hydrogen will never, ever, ever be the central atom. Just like carbon will always be the central atom. Once we develop the skeletal structure, then we're going to start distributing our valence electrons determined in step 1. We start by drawing a single bond between each of the outer atoms and our central atom, and we subtract 2 for each bond we draw. Now, when you subtract out that number, if you reach 0, then you check, does everybody have an octet? If you don't reach 0, then the next step is to give the outer atoms an octet. And then you ask yourself, does everybody have an octet? We're going to keep coming back to that question a lot. Does everybody have an octet? If not everybody has an octet, that's when we start making multiple bonds between the outer atoms and the central atom, because ultimately everybody must have an octet except for hydrogen and boron of the nonmetals and metalloids. So anyhow, we're going to be using this document. And then the other thing that's going to come up today is step number 7. And that is there is going to be the potential that we will draw resonance structures. And I'll explain a little bit more about resonance structures when we get there. Some of this information is the same information that I've already given you in the lecture, but there is also this very neat periodic table that you'll find at the end of that document that describes the number of bonds each element tends to like to have. And so you'll find that this helps you in determining if you've given the elements their correct number of bonds. So anyhow, we're going to be using this document today during the remainder of this process. I don't know what NaSl is, Kara. That is not a term I have heard, so I don't know if that's going to be something that will work or not. Maybe as I go through this, you can tell me, since that's an acronym I am unfamiliar with.
Sorry, my thing kind of logged me out, but it's a rule used in AP chemistry, and it's for drawing structures, and it was needed, available, and it just has to do with like the different atoms, valence electrons. But I couldn't
It,
remember what the last two stood for, so I thought you might, but that's okay if you don't.
it's not a term I've actually heard before. So, but it could very well be. Okay, so let me get back to sharing my screen, my iPad, which I think needs to be charged. That's going to be fun. Come on. There we go. Well, let me make sure I'm recording. Okay, good. Okay. So Lewis structures of covalent molecules. Again, I'm going to basically be using that document in determining the Lewis structure for a variety of molecules. The first one we're going to do is methane. So we have one carbon atom and we have 4 hydrogen atoms. Carbon is in group 14, so it is going to bring with it 4 valence electrons. Hydrogen is in group 1, the last digit of 1, so it's going to bring with it 1 valence electrons. So the carbon contributes 4 and all of the hydrogens contribute 4 for a total of 8 valence electrons that must be distributed. The next thing we are to do is we are to develop the skeletal structure. Again, hydrogen will never, ever, ever be the central atom. So our central atom is going to be carbon, around which we are going to place the hydrogens. The next step says to distribute your electrons. The first thing we're going to do in distributing our electrons is we're going to share a pair of electrons between each of the outer atoms and the central atom. And we're going to subtract 2 for each bond we draw. We drew 4 bonds. 4 times 2 is 8. So we'll subtract out 8 electrons due to bonds. And we have hit 0. Again, anytime you hit 0, your first question should be, does everybody have an octet? The hydrogens only require 2, and each hydrogen atom currently has a share of 2 because it has a single bond that it gets the share of. So yes, your hydrogen atoms have 2 valence electrons. Your carbon atom wants a share of 8. It must have an octet. And because of the 4 bonds, it has a share of 8. So that means that the Lewis structure for methane is indeed your carbon atom single bonded to 4 hydrogen atoms, because every single element has its octet. And every single valence electron has been distributed. Let's look at another example. Let's look at water. Water has 2 hydrogen atoms. Hydrogen is in group number 1. The last digit is a 1, so they contribute 1 valence electron. We have 1 oxygen atom. Oxygen is in group 16. The last digit is 6 for 6 valence electrons. So the hydrogens contribute 2 and the oxygen 6. for a total of 8 valence electrons that must be distributed. Now, we develop our skeletal structure. Again, hydrogen is never the central atom. Therefore, it must be oxygen around which we're going to place our hydrogen atoms. The next thing says to distribute your valence electrons. We start by drawing a single bond between our outer atoms and our central atom, and we subtract 2 for each bond that we drew. We drew 2 bonds. 2 times 2 is 4, so we will subtract out 4 electrons due to our bonds. That leaves us 4 valence electrons to distribute. When you have valence electrons still remaining, the first thing you do is you give your outer atoms an octet. Well, hydrogen only requires 2, and it has its 2. So hydrogen is perfectly content right now. If electrons still remain after your outer atoms get an octet, then the remainder of the electrons go on the central atom in pairs. So we're going to place the last 4 electrons on our central atom in pairs. And we hit 0. Anytime you hit 0, you ask, does everybody have an octet? The hydrogens have their version of an octet. They have 2 because they have 2 within the bond. The oxygen has 8. It has 4 within the bonds and 4 in the lone pairs. So it has an octet. Therefore, the structure of water, the Lewis structure of water, is indeed oxygen single bonded to 2 hydrogens, and on that oxygen are 2 lone pairs. Let's look at another example. Let's look at methyl chloride. First thing we need to do is determine our number of valence electrons. We have 1 carbon. Carbon is in group 14. The last digit is a 4, so it has 4 valence electrons. We have 3 hydrogens. Hydrogen is in group 1. The last digit is a 1, so it has 1 valence electron. And we have 1 chlorine. Chlorine is in group 17. The last digit is a 7, so it has 7 valence electrons. Adding up the total valence electrons, we will need to distribute 14 valence electrons. The next thing is to develop your skeletal structure. Typically, the first element listed is going to be your central atom. This is particularly true if that first element listed is carbon, because carbon is always the center of attention. So we're going to place carbon in the center, and we're going to place our other elements around that carbon. Now we start distributing our valence electrons. We start by drawing a single bond between the external atoms and the central atom. And we subtract 2 for every bond we drew. We drew 4 bonds. 4 times 2 is 8. So we'll subtract out 8 valence electrons. And therefore, we still have 6 to distribute. The next thing says to give your outer atoms an octet. Well, your hydrogens are already content. Your hydrogens have 2 valence electrons. They are content because that's all they want. Your chlorine, however, is going to want electrons because it must have an octet. and right now it only had 2. So we're going to add 6 more electrons to the chlorine, because by adding 6 electrons to the chlorine, now our chlorine has an octet. We will subtract out the number of electrons added, and we have hit 0. When you hit 0, you cannot add lines, you cannot add dots. All you can do is alter what is there. When you hit 0, that is when you check, does everybody have an octet? You know your hydrogen does, you know your chlorine does. The next thing is your carbon. And your carbon also has an octet because it has 8 in the bond. So everybody here has its octet. And therefore, the Lewis dot structure for methyl chloride is going to be one where the carbon is single bonded to 3 hydrogen atoms, and it is single bonded to a chlorine atom, and then on that chlorine are 3 lone pairs. Let's look at another example. Let's look at hydrogen cyanide. We have 1 hydrogen. Hydrogen is in group 1. The last digit is a 1. So it has 1 valence electron. We have 1 carbon. Carbon is in group 14. The last digit is a 4, so it has 4 valence electrons. And we have 1 nitrogen. The last digit is a 5, so it has 5 valence electrons. So between our 3 elements, we need to distribute 10 valence electrons. Okay. Now we develop the skeletal structure. Hydrogen is never the central atom, but carbon always is the central atom. So we're going to place carbon, and then we're going to surround that with nitrogen and hydrogen. Once you do so, you are to draw you are to distribute your valence electrons. We distribute our valence electrons by starting with a single bond between the external atom and the central atom, and subtracting 2 for each bond we drew. We drew 2 bonds. 2 times 2 is 4. So we'll subtract out 4 due to our bonds. That leaves us 6 valence electrons still to distribute. Once you've drawn your bonds, the next thing that is stated is to give your external atoms an octet. Your hydrogen currently has 2. That is all that the hydrogen needed. But your nitrogen is lacking. Therefore, we are going to put 6 valence electrons on our nitrogen. That leaves us 0. When you hit 0, you ask, does everybody have an octet? Your hydrogen does. Your nitrogen also has its octet because it has 8 valence electrons. But your carbon does not have an octet. Your carbon currently only has 4 valence electrons. Therefore, no, not everybody has an octet. Now here is where step 4 comes into play. If you have hit 0 and not all atoms have an octet, then you are going to share a pair of electrons from the outer atom with the central atom. So we are going to bring in a pair to share between the outer atom and the central atom. When we do so, the structure that arises is this structure. Now, anytime you change the structure, you ask, does everybody have an octet? Your hydrogen does. It has 2 valence electrons. It is still content. Your nitrogen still has 8 valence electrons because it has 4 within the lone pairs and 4 within the double bond. But your carbon currently only has 6 valence electrons. So no, not everybody has an octet. So we have to repeat step 4, which says if your central atom does not have an octet, then you are going to share a pair of electrons from the outer atom with the central atom. When you alter the structure, you should check, does everybody have an octet? Your hydrogen still is content because it has its 2 valence electrons. Your nitrogen has 8 valence electrons. It has 2 in the lone pair and it has 6 in the triple bond. And your carbon now has an octet because it has 6 in the triple bond to nitrogen and it has 2 in the single bond to hydrogen for a total of 8. And this is the Lewis structure for hydrogen cyanide. Okay. Now, we've talked about the fact, or we've been talking about polyatomic ions. Polyatomic ions are a substance that straddles the world of ionic and covalent. They are ionic because they are charged. But they are covalent because the atoms themselves are bonded through covalent bonds. So polyatomic ions straddle this world of ionic compounds and covalent molecules. Now, being ions, if you go back to one of the, when we started talking about ionic compounds today, being ions, when we developed the Lewis structure for a polyatomic ion, the polyatomic ion will go in brackets with the charge as a superscript to the right. Now, being a covalent molecule, we are going to treat it like we have been treating the remainder of the covalent molecules, where the first step is going to be to determine the number of valence electrons. But here is where polyatomic ions differ slightly from covalent molecules that we have discussed thus far. The covalent molecules that I have discussed thus far were neutral compounds. But now we're dealing with covalent molecules that are ions. What it means is when we develop the number of valence electrons to distribute in our molecule, we are going to have to take into account the charge. Again, when we develop the number of electrons to go into our molecule, we are going to have to take into account the charge. To see all this in play, let's look at the polyatomic ion nitrate. Nitrate contains one nitrogen. Nitrogen's in group 15, the last digit of 5, so it has 5 valence electrons, and it contains 3 oxygens. The last digit of their group number is a 6, so it contributes 6 valence electrons for a total of 18 valence electrons. The atoms themselves contribute 23 valence electrons. But this negative charge means that we are going to add electrons to the total valence electrons. In this case, we are going to add 1 valence electron for the charge. So we actually have 24 valence electrons to distribute. The next step in the development of Lewis dot structures for covalent molecules is to develop the skeletal structure. The first element listed is going to be your central atom, around which you're going to place all other atoms. We now need to start distributing our valence electrons. We start by drawing a single bond between each of the outer atoms and the central atom, and we subtract 2 for every bond we drew. We drew 3 bonds, 3 times 2 is 6, so we will subtract out 6 valence electrons due to our bonds, leaving us 18 valence electrons still to distribute. When valence electrons still remain, you make sure that your outer atoms receive an octet. Currently, each oxygen has only 2 valence electrons found within the bond. For each oxygen atom to receive an octet, each oxygen needs an additional 6 valence electrons. There are 3 oxygen atoms, each requiring 6 valence electrons, for a total of 18 valence electrons.
Okay, bro.
For our outer atoms.
Yes, bro. So
please turn off your mic.
I am so sorry.
It's okay. And we hit 0. When you hit 0, what is the question? The question is, does everybody have an octet? And the answer is no, not everybody has an octet. Your oxygens each have 8 valence electrons, 6 in the lone pair and 2 in the single bond. But your nitrogen currently only has 6 valence electrons. So that means that not everybody has an octet. When your central atom does not have an octet, it means that you're going to bring in a pair of electrons to share between that outer atom and that inner atom and that central atom. And the structure that results is this structure. Anytime you alter the structure, the first question you're to ask is, does everybody have an octet? Your single bonded oxygens do have an octet because they have 6 valence electrons in their lone pairs and 2 in the single bond. Your double bonded oxygen also has an octet because it has 4 electrons in the lone pairs and 4 electrons in the double bond. And your nitrogen also has an octet because it has 8 electrons found in bonds. So that being said, this is a Lewis dot structure for nitrate. To finish it out, we would put it in brackets with the charge as a superscript. Anyone have a question so far about nitrate? Well, I have one. Is there a reason I used the bottom right-hand oxygen? Could I have done anything else? The answer is yes, I could have and should have done something else. When you make a choice of an outer atom to share a multiple bond to give everybody an octet, and there could have been an equivalent choice, then what it means is that you should actually write a resonance structure. Again, if you make a choice of an outer atom to share a multiple bond with, and you could have made an equivalent choice, that means that the molecule should actually be a resonance structure, and you should draw the other options as well. We draw the other resonance structures and we separate them by a double-headed arrow in order to obtain the true Lewis structure. Technically, what it means with that double-headed arrow is that the true Lewis structure is not any one form. It is somewhere in between. So the one that I drew, where I had the right hand bottom oxygen making the double bond, that is but one form that I should draw for this molecule. The other forms come back to our original here. The second form that I should draw would assume that the top oxygen shared its electrons. If I assume that the top oxygen shares its electrons, then the structure that is obtained is this structure. But there is still one more option here. And that is the bottom left oxygen could be the one that's shared, in which case there is one more variation that I must draw in order to draw the Lewis structure. So again, nitrate is an example of a resonance structure. A resonance structure will arise anytime you make a choice, and an equivalent choice could have been made. When that occurs, you have to show all of the options. In order to properly illustrate the Lewis structure for that compound. The other thing about, again, polyatomic ions are covalent molecules that have a charge. We will get into why they have a charge next Wednesday when I discuss the last variation on the Lewis dot structure, which takes into account expanded octets and more specifically formal charge. So I'll get into why they are charged ions when we start discussing that. I think I've given you plenty to think about the day before an exam. Thankfully, this isn't on the exam. This will be on your third exam. But given the fact that you do have an exam to study for, I am not going to keep you the entire time. I am going to let you get back to studying. So what I will do is I will end the lecture here for today. On Wednesday of next week, we will pick up we'll pick up some more in Lewis dot structures, and then we'll start talking about VSEPR theory. So we've got a busy week next week. That is a lab lecture again. But otherwise, I will see you tomorrow for the exam, and I will stay on and answer questions if questions arise.